All right, so for the next step of the problem, we need to realize that we have our first eigenvector and our eigenvalue found already. That's the -1 value and this vector. But now we need to go ahead and find the two solution vectors created by this one complex number. So remember again that we have our y of t is equal to e to the lambda t times v. So that's e to the 2it times this vector, that's -2, -1 minus I, and +2. We now need to rewrite the e to the 2it as the cosine of 2t plus I times the sine of 2t, and take that and multiply it times our vector -2, -1 minus I, and 2. So this is going to get a little big before it gets smaller again. We multiply the -2, that's pretty simple. That's -2 cosine of 2t minus 2I sine of 2t. For the middle entry of the vector, we're going to have to use FOIL to multiply it out. So that's going to be the negative cosine of 2t from the outside. And then we're going to have a minus I cosine of 2t. And then we're going to have a minus I sine of 2t. And then we're going to have a minus I squared sine of 2t. And then for the bottom entry, that's just 2 cosine 2t plus 2I sine of 2t. And then just like before, we need to split this apart into a real and imaginary vector. So for our first vector, the real one, that's -2 cosine 2t, and then negative cosine of 2t. And then that minus I squared sign becomes plus the sine of 2t. And then we have a 2 cosine of 2t for our third entry. And that's plus I then times the imaginary part, which is -2 sine 2t, negative cosine 2t minus the sine of 2t. And then for our last entry, 2 sine of 2t. So again, those two vectors there are the second and third vector that we need to express our general solution. So let's go through and find that general solution. It's going to have our first arbitrary constant c1 times e to the lambda t, which is -t, times the eigenvectors 0, -1, 1. And then we're going to have a second arbitrary constant c2 times that first vector, -2 cosine 2t, negative cosine 2t minus, actually that is a plus sine of 2t, and then a 2 cosine 2t, and then a third arbitrary constant, c3, times our -2 sine 2t, negative cosine 2t minus sine of 2t, and then 2 sine of 2t. And that right there is our third vector. And so now we've got our three solution vectors and our three arbitrary constants. And yes, you could actually go in and verify the linear independence of these three vectors. Would not be a lot of fun. And you could also go ahead and verify that they're solutions by going through and multiplying a times y and showing that it equals the derivative y prime.